Okay, hello again, everybody. So what remains to us this week is to complete the proof of Lagrange's theorem, and that means basically proving a technical property about left cosets that we used in the final step of the proof in the last lecture section. So what we need to prove is this statement, which is lemma 2.1.7 in the lecture notes, and I really encourage you to study section 2.1 of the lecture notes carefully. That's really the sort of authoritative document for us on this topic, rather than these slides, which are sort of an abridged version. So what the lemma says is that if we're in the situation of Lagrange's theorem, so we have a group G, we've got a subgroup H of G, and we've got a pair of elements of G in mind, G1 and G2. What we need to show is that the cosets, the left cosets of H determined by those two elements, G1H and G2H, that those two subsets of G, if they have anything at all in common, anything at all in their intersection, must actually be the same set. Okay, so the lemma says cosets of a subgroup determined by different elements are either identical, they're the same set, or they're completely apart from each other with nothing in their intersection. Again, this is the key sort of, I suppose you could think of it as sort of a geometric property of cosets that enables us to prove Lagrange's theorem by building up the group G as a collection of cosets of the subgroup H that have no elements in common with each other, so that we can conclude that the number of elements in G is the number of elements in H plus the number in the first coset of H, which is the same as that, plus the number in the next coset of H, which is the same again, and so on, so that it's a multiple of the number of elements in H, which is exactly what Lagrange's theorem says. So that's what we have to do. That's our task. Of course, it's not true in general that if you take any pair of subsets of a group, that you don't expect them to be either disjoint from each other or to be identical. You typically might expect that they might have some stuff in their intersection, but not everything. So if this statement is true, it must be true because of the fact that H is a subgroup of G and not any old subset of G. And we must try to use our knowledge and definitions of groups and subgroups to prove the statement. Okay, just a remark, our goal here in proving this lemma is to show that two subsets of a group G are equal to each other or disjoint from each other. So the general sort of strategy to show that two sets are equal to each other, of course, what it means for two sets to be equal to each other is that they have exactly the same collection of elements. So in general, in any area of mathematics, if you have a need to show that two sets A and B are actually the same set, then what you need to do is show that every element of A belongs to B, so that A is a subset of B, and that every element of B belongs to A, so that B is a subset of A. So that's kind of the standard framework for trying to show the two sets are equal to each other in whatever context you're in. In this case, what we need to use to apply that standard framework is the properties of groups, subgroups, and cosets. Okay, so that's our goal. We're going to try to prove this lemma. Okay, so to construct our proof, well, we've got our two cosets, G1H and G2H. G1 and G2 are fixed elements of G. H is a subgroup of G, and we're looking at the cosets G1H and G2H. What we need to do is show that if they have any element at all in common, then they must be the same set. So if they have no elements in common, that's fine. In that case, they're disjoint. The theorem is satisfied, and there's nothing for us to do in that case. We must worry about the case where they do have something in common, because that's the case where we have to actually show something, that they are in fact the same set. So let's suppose these two sets, G1H and G2H, do have at least one element in their intersection. That means there's an element that belongs both to G1H and G2H. The fact that this element belongs to G1H means that it has the form G1H1 for some element H1 of H. The fact that the same element belongs to G2H means it has the form G2H2 for some element H2 of H. So what we can say is that there's a pair of elements H1 and H2 in the subgroup H with the property that G1H1 is equal to G2H2, and the sort of multiplication here is just the operation in the group G. Okay. From that, our task is to deduce that the sets G1H and G2H are equal. In other words, that every element of G1H is also an element of G2H, and that every element of G2H is also an element of G1H. We'll do the first of those first. We'll try to show that every element of G1H belongs to G2H. In other words, that G1H is a subset of G2H. So let's give ourselves an element of G1H. Okay, we have to ask ourselves, what does it mean to be an element there? It means that you are some element of H composed on the left with G1. Okay, so a typical element of G1H, that coset, is G1 composed with H for some element H of the subgroup H. Okay, what are we supposed to do with this to show that it must belong to G2H? Well, the only thing that we have in our hands that relates G1 and G2 really is this equation. So let's see if we can use that somehow. We know that G1H1 is equal to G2H2 for some fixed elements H1 and H2 of H. We can rearrange that by composing both sides of it on the right with the inverse of H1 to say that G1 is G2, H2, H1 inverse. Okay, so if you're in doubt about what's happening here in this implication, look at the left-hand side. Okay, that came from the hypothesis that the two cosets of H determined by G1 and G2 have some element in their intersection. That's an equation. If we compose both sides of that equation on the right with the inverse of H1, then that cancels the H1 here. And on the left, and on this side, it gives us G2, H2, H1 inverse. So we're left with G1 is equal to G2, H2, H1 inverse. I should be careful for people like myself who are sort of hung up on the rules here. The fact that I can write G2, H2, H1 inverse just as a product of three things like this without worrying about where the brackets go is because I know that the operation is associative. So here, although it's implicit, it's not highlighted in the text, we are actually using the associative property of the group G to write down this product G2, H2, H1 inverse without worrying about where the brackets are. Okay, so what the point is, the element G1, it follows from this equation that G1 can be expressed in terms of G2 and elements of H. G1 is G2, H2, H1 inverse. What we're trying to do is show that the element G1H belongs to the coset G2H. So if this is G1, then G1H is that element composed with H. So again, using the associative property, this is G2 composed on the right with H2, H1 inverse H, that product of three things. Now is the point where we must appeal to the fact that H is not just any old subset of G, but it's a subgroup of G. We know that the elements H2, H1, and H all belong to the subgroup H. H is a subgroup. That means it's closed under taking inverses. So it contains the inverse of each of its elements. So if H1 is an element of H, then H1 inverse also is an element of H. Not only that, but if H2, H1 inverse, and H are all elements of H, then the elements that we get by composing the three of them under the group operation is also an element of H. So what we're saying here is that G1H, this typical element of the coset G1H, also has to form G2 multiplied by something that's in H. And that's what it means for this element to be in the left coset of H determined by G2. So what we've shown is that every element of G1H also belongs to G2H, so that G1H is a subset of G2H. There's quite a lot going on there, and it's making full use of the fact that H is a subgroup of G, and also of the definitions of the cosets of H determined by G1 and G2. So, you know, there is a lot there, and what's really needed to follow the steps of this proof, I think, is a sort of complete familiarity with all of the definitions of subgroups and of cosets. Okay, so we've successfully shown that G1H and G2H, G1H is a subgroup of G2H. We still have to show that G2H is a subset of G1H, but what we need there is really exactly the same thing here. When we had this equation, we sort of privileged G1 by using it to write G1 in terms of G2 and elements of H. We could have chosen G2 and written it in terms of G1 and elements of H, and taking that approach would have allowed us to show that every element of G2H belongs also to G1H. So to complete the proof, we need to show the opposite inclusion. So starting by rewriting our equation relating G1 and G2 in the other way, by expressing G2 in the form G1H1, H2 inverse, then looking at a typical element of the coset G2H, replacing G2 with this expression, we can show that every element of the coset G2H also belongs to G1H. Then we've concluded that each of these two sets is a subset of the other one. In other words, they're the same set. And our conclusion is that the left cosets of H in G, determined by different elements, if they intersect at all, if they have anything in their intersection, are identical. The other possibility is that they have nothing in their intersection and they're completely separate. And in that case, the total number of elements in their union would be twice the number of elements in the subgroup H. So this property really is the key property that allows us to prove Lagrange's theorem by expressing the group G as the union of disjoint left cosets of its subgroup H. So remember there, the starting point was that we had a finite group G and a subgroup H of G. Okay. We were able to kind of build G up in this kind of ladder by starting with the subgroup H that accounts for some of the elements in G. If it's all of them, great. In that case, the order of H certainly divides the order of G. If H is not all the elements of G, then there's some element X, which isn't in H. Okay. The coset of H determined by X is not the same as H because it includes the element X, which isn't in H. That means it must be completely disjoint from H. So it's another sort of copy of H with the same number of elements that's contained in G. If the union of H and the first coset there, XH, is still not all of G, then there's some element Y that's outside both of them. We add in the coset determined by Y, That includes the element y, so it's not the same as the coset determined by x. That doesn't have y in it. It's also not the same as h itself. So it has no intersection with either of these two. That means it's completely separate from both of them. It's another slice of the group G that contains the same number of elements of H, and so on. We continue this process until we can't continue it anymore, until we've filled up the whole group G. And our conclusion then is that the total number of elements of G is the sum of the numbers of elements in all of these slices, which are the distinct cosets of H and G. And if that's true, well, each of these things has the same number of elements in it as H does. So the total number of elements of G is the number in H plus the number in H again, plus the number in H again, and so on. It's K times the number of elements in H, where K is some integer. And just to note, the name that's given to that integer is called the index of the subgroup H in the group G. So the index of H and G in general is the number of distinct cosets of H and G. That can be a finite number even if the groups are infinite. In the case of Lagrange's theorem, of course, we care about the case where they're finite. The index of H and G is denoted by G colon H like this, enclosed in usually square brackets. And if G is finite, then of course G, the index of H and G, is also equal to the fraction number of elements in G divided by the number of elements in H. There's a vertical bar missing there. This is the number of elements of G divided by the number of elements in H. Okay, so that's the sort of key property of cosets that goes into Lagrange's theorem. There are a few more bits and pieces that could still be tidied up, and those are all to be found in section 2.1 of the lecture notes. So please do study that section of the notes in detail. Lagrange's theorem is really well, one of the highlights of our course. It's one of the really key fundamental theorems in group theory. It goes back to Lagrange in the 18th century, but Lagrange sort of, it's attributed to Lagrange, although he didn't really prove it in the sense that it's recognized today, because he did it without the definition of a group, and he was working with systems of polynomials with multiple variables and looking at what happens when you permute the variables. But he came up with sort of a special case, I suppose, of what's now recognized as Lagrange's theorem. The first sort of complete proof of it was given by Jordan in around the middle of the 19th century. So it does go back quite a ways, but its modern formulation is probably unrecognizable to its original authors because the fully abstract definition of a group hadn't really been invented yet at that point. Okay, our challenge for this installment, our second challenge for this week, is really to kind of think a little bit about a potential converse to the lemma that we've just talked about. So I suppose what I'm getting at here is to ask you to think about, in the proof that we just gave of the fact that cosets of a subgroup in a group determined by different elements are either distinct from each other, completely disjoint from each other, or else completely coincide. To what extent did that really depend on the fact that the thing we started with was a subgroup and not just any old subset of the group? So for any subset S of a group G and any element X of G, you can define a notion sort of analogous to the notion of a coset by just saying, you know, we can take all the elements of S and compose them all on the left with X, and we can call that thing XS. It's, you know, if S happened to be a subgroup, this would be a left coset. For any old subset though, we can do it. And your challenge is to suppose that you have a subset of a group G that has the property that we described in our lemma. Namely, that whenever you take different elements, X and Y of G, and look at the copies of the subset S, sort of translated by X and by Y, if you find that for all choices of the elements X and Y in G, those two sets are either the same or they completely miss each other. So if you find that whenever they have anything at their intersection, they're actually equal, does it mean that S must be a subgroup? Okay, we know that's true if S is a subgroup. That's what we just proved. But if it's true for some subset S, does it mean that S is a subgroup? So my suggestion is, suppose you have a subset with that property, and suppose also that S does contain the identity element of G. Okay. Must it be true in that case that S is a subgroup of G if it satisfies the condition of our lemma from this lecture? Okay, so the answer to this question should be either a proof that yes, S must be a subgroup of G in this situation, or a counterexample, an example of a subset S that contains the identity in some group that isn't a subgroup but satisfies the property of the lemma. So I think it's quite a tricky challenge, but I'm sure that if you study the lemma carefully and give it a shot, you should hopefully be able to make some progress on it. Okay, if you have time to have a look at that, that would be great. If not, don't worry, the challenges are there when they're of interest to you, and there's no obligation to do all of them. So have a go at it if it interests you. Thanks a lot, everybody, and see you later.